All right, so today we are going to continue that whole issue. Hi, good morning, Akim. Just out of curiosity, and I should know this, are any of you all not in Trinidad? Mario, where are you?
Please.
Ah, okay, great. And Jamal, where are you? Barbados, Zidane, where are you? Don't tell me France. St. Lucia. Okay, great, excellent. So, well, I hope you all are able to participate well. The connections and the access to materials are working for you. And of course, let me know if there are any difficulties or any situations that arise where you can't get the material or you can't get access. Are all of us on the same time zone? By any chance?
It's 6 a.m. here, so
All right, that's okay. That's nice. That's nice. So that means you have to get up. You have to get up at least 5 to 6, right?
5:30 actually because I have to mix coffee, you know.
Yeah. Oh well, that's life. But at least you'll be able to attend classes right now and participate, and hopefully everything is going well. Yeah.
Yes, I'm
Um,
I'm glad.
yes, excellent. All right. But again, if there are any difficulties from any of you all, let me know, please, and we'll work it out as best as we can. All right. So today we continue this the discussion on convolution. Remember when we ended last week Tuesday, what we did is that we introduced how what exactly convolution meant and how it arose. And it basically arose because of the input and output relationship for a system, whether it's a continuous time or a discrete time system. The relationship between the input signals and the output signals are that the output is a convolution of the signal going in and the system response. If we do it with the Laplace transform, it was nice first because the convolution there just turned out to be the product of the system transfer function, right, which was this bit. If the system is ht, the transfer function is hs, and the Laplace transform of the input. So at that point in time, you can work and you can evaluate the response for the system. And then at the end, when you get that, you could come back into time. There are some cases that we said they are not always the easiest to evaluate in the Laplace domain. And so what we did is that we looked at the mechanics of how the convolution came about. And we saw that in the Laplace domain, it's a product, but in the time domain, it's this integral, right? So it's an integral where in time, and time is going from minus infinity to infinity. And we're taking the integral of the input and the system. And this is what we're going to try to figure out how to do it today, right? And we'll see exactly, I mean, it's not always necessary to do it, but you need to be aware that at some point in time, these things arise and a mechanical um, sit down and do it with pen and paper might be the only way to solve a particular issue that is arising. Okay, so again, if anything, as we go through the discussion, you have the handouts, you have the notes, sorry, the slides, and if as we go through the discussion, if at any point in time something doesn't make sense, of course, get my attention somehow, right? Put a question in the chat, raise your hand, or just say a word, a polite word, of course, and then we'll stop. All right. So here we go. So let's see how what it. Let's look at the integral itself and just break it apart and see first off in terms of what it means, how you evaluate it. Of course, the integral itself is two functions. Yeah, there's two functions, x and h, And what it does, first off, we start off with it with x at t and ht. Then the next step is that we have, okay, so we have the functions here. I've drawn some arbitrary functions here. They're arbitrary so that, of course, at this point in time, we have no idea what describes either x or t. This is just a graphical interpretation of how the convolution integral is to be evaluated. Right, so you have xt, you have ht. Lord knows how they look. We have some representations here for them. The step is, of course, the integral. Remember, the integral is a function of tau. Why? Let me just go back a little bit. In the variable of integration here, what happens if you remember from your calculus? If you are integrating with respect to time and you have some limits that are going here, mathematically it is not correct, really and truly it is not correct to do something like this. Really and truly, you're not supposed to integrate. You're not supposed to integrate with respect to well, some time or whatever it is you're integrating with respect to, while the limits themselves are potentially variable. So like in here, we don't know what, if I were to give you this, you don't know what T1 and T2 are. So integrating T at the same time you have some limit that is a version of T is not mathematically correct. So what we normally do is to change this variable to some other thing, right? In our case, the closest Greek letter to T, of course, is tau. So we would integrate with respect to tau and then substitute for the T's as well, okay? Here, you have both of them inside of here. This is just to confuse the matters a little bit more because T is the one that is variant, tau is the one that we integrate in with respect to. Let's see what that means, okay? So you have the two functions. The next step, of course, is to change the variables to the variable of integration, which is tau. All right. Once you have that now, so let's look at h of tau. H minus tau is, of course, that particular signal reversed or flipped along the tau equal to 0 axis. So if h of tau is this, if h of tau is this one here, then h minus tau is h of tau flipped around the axis here. So in other words, tau 1 goes to here and tau 2 goes to here. Okay, fair enough? And then h t minus tau. Remember, t is the variable that we vary in. That could be a number or it could be an arbitrary variable that going along the place. If I were to ask you, what is h3 minus tau? Right? Where would that be? Where would I shift the t? Where I would shift h of minus tau to at that point? Would I go to the right or to the left? Yeah, okay, well, right. Okay, so we have two rights and a left. So as I said, the way to look at that is that you look at where is h0. H0 would be at this point at tau equal to plus 3. Yeah, tau equal to plus 3. So in other words, plus 3 would have been to, would have been to the right. Yeah. And similarly, if I ask you where h of minus 3 minus tau would have gone to the left. Always look to see where the middle point is shifting along. So if that is the case, we are integrating. Remember, the function is x tau ht minus tau. So ht minus tau is going to be this thing moving up and down the axis depending on where the value of the t is. Fair enough? Everybody following? Right? This is drawing back on what we did early on a couple of weeks ago when you moved things up and down the axis depending on where the index was. It either was a delay which moved to the right or an advance to the left and that kind of thing. All right? Right, so look at the integral now. So the integral now is the integral of x tau. X tau is this one, right? The same xt, we just changed t to tau. Ht minus tau, remember, ht minus tau is h of tau flipped around, and then it is somewhere along the time axis depending on the value of t. And t is going to take values that is going to run from minus infinity to plus infinity. So in other words, ht minus tau, which is the yellow signal here, is going to start as t varies. If you imagine what's going to happen, we need to evaluate this as t runs. It's a continuous integral, so as t runs from minus infinity, so this thing is going to go start from minus infinity, and then it's going to slide all the way across. So at some point in time, if you think about it, depending on the value of T1 here, at some point in time, there's no interaction between H and X. Then at some point in time, T minus tau starts to overlap with X of tau. At that point in time, that is when you have the integral. Remember, the integral is a product of these two things. So if they never overlap, if they never occupy the same space, the same interval in time, then you can't have a product. Okay, so it's sliding. Eventually, H and X start to overlap, and then while they overlap, you evaluate the integral, and then as ht minus tau is moving along, as it moves along, you evaluate all the way through, and then eventually at some point in time, H going to be something like this, and there will be no overlap here any longer, and the convolution ends. Make sense? Yeah? So the process is what is in the green, is in that green box. So you have the signals X and T, X, sorry, and H. You flip around one, you change a variable from t to tau, you flip it around, one of them, then you slide the ht minus tau along the axis, the time axis, and then you are, wherever they integrate, they overlap, you find the product and you integrate that. And that's your convolution at the end. So we'll work it through by some examples and see what happens. So here's a little bit of it's a contrived example, but it's the kind of thing that you're going to meet when we do block diagrams and so on. So here is a temperature, so something that's controlling a temperature. We have a gain block, we have an integrator block, we have a summing node. This here, so we have some input and we have some output. It's a temperature, whatever that is. Could be an incubator, could be an oven, something to keep your coffee warm, whatever it is. And you know already, I mean, just conceptually, you know, a gain block, there's a basic amplifier, right? An integrator block, you know, we can make that with op amps and capacitors now. And there we are taking the signal and we sending back some of the signal back to the input. And we call this, anybody remember what we call this particular relationship? We have the input coming in and it's a positive, and we have the signal coming back from the outside and it's a negative. We spoke about that before. Remember what it was? Those of you in the electronics class too, we spoke about that. Negative feedback. There we go. Right, so it's a negative feedback system. So what it is doing is taking the output, subtracting it from the input, and then using this thing here, that difference to make the thing work. Of course, as I say, this is just simple because we haven't gotten into block diagrams as yet, and you haven't done control systems as yet. So it's a very high level, what do you call it, diagram that we're dealing with here. So if you want to just run through in terms of what the algebra is telling us, if the particular signal here, AT, is the difference between xt and yt. That is going through the block K. So at the output here, you have basically Ka of t. And then Kat goes through an integrator block and it's integrated. And then you get y coming out. So why is that? Y is in fact this, and that is also subtracted from x. So this is what the relationship between y and x looks like. And correctly speaking, I should really have y tau here, okay? Because we're integrating with respect to, we can't integrate with respect to t if one of the variables of integration, one of the limits of integration is also t, right? So mathematically, more correctly, this should be y tau is equal to that expression there, okay? You're not going to get penalized by putting it, saying yt is so on. But when you're doing the convolutions, remember you're going to have t's in the middle of there. So you don't want to have a t in the wrong place, right? So if, for instance, if I had xt and yt inside of here and integrating and substituting t, I might run into problems, okay? So at that point now, so the input-output equation is this. So if you want to find, let's say now that this is a diagram, and you want to find the impulse response, or you want to find what is the temperature change, if the gain is a half, and you put a step change of 0.75 degree after 4 minutes, right? So it's a very slow-moving kind of temperature system here. And the particular thing is to evaluate how the system works, which is the kind of issue that you have in to deal with. So, well, of course, if you're given the input-output equation, to solve that, the first thing you do is to differentiate, so to get rid of the integral sign. And then the impulse response, of course, xt will be delta t. And if you run through this is a first-order differential equation. So the impulse response of it looks just like you would have for the RC circuit. Some k e to the minus in the RC circuit, it will be t over RC, the minus t over RC. Here it is kt, whatever k happens to be. K is the gain of the system, and they told you k, I think, is 0.5. All right, if I'm not mistaken, k is 0.5, yeah. All right, so that's fine. And we have ut because we're saying that the system, when you put ut on the response for a system, what are you saying? We said we did that for a particular reason, to make sure of something. Anybody remembers what it is? We did ut to make the system behave in a particular way. Remember the terminology? Yeah, ut is a unit step, but when we this is the impulse response, but we're putting a unit step here for a particular reason. Yeah, we put ut to indicate that the system is causal, meaning that is not going to do anything until we put an input into it or until we switch it on. Right? If you don't put anything on it, it means technically it could be doing things even without us knowing, which is not predictable. Right? So when you put UT, when you have a system, this is the system response, the impulse response for the system is HT. Right? So the HT, now we're saying it is a causal system. So the impulse response, the system is not going to respond until we put anything into it. So what's the, go back here now, and this is what they're saying. So the gain is 0.5, and then we're putting a step change of 0.75 at t equal to 4 minutes. So this is my input. Xt is a unit step after t equal to 4 minutes. Is going to go from 0 to 0.75. Right? So this is the input here. Right? Ut minus 4 mean t, the input is occurring at t equal to 4. And ht, which we just evaluated, right? If k is 0.5, ht is 0.5 e to the minus 0.5 t. Once t is greater than or equal to 0. If it's less than 0, nothing happens because we want the system to be causal. Fair enough, and notice the greater than or equal. We assume that the system doesn't do anything, but it actually changes, or the response starts at t equal to 0. Okay? Yeah? Maybe? No? Right. So graphically, this is the system. Graphically, this is what we have. So if I want to evaluate the output of that, the output is going to be the convolution of xt. The output, therefore, is the convolution of x tau h t minus tau d tau. Right? That is my output. And this is what the second part of the question. So you have a system whose response looks like that. You have an input where the response is happening, like that, a step response, and I want to see what the output does. So let's do this graphically. As we said, first off, the first thing that you do is we have h tau, we need to find ht minus tau. Ht minus tau, if clear this annotation here a little bit. So if h of t is that, h of tau is also going to be the same thing. Let me just get a different color here. H tau is also going to be this, and ht minus tau will be this flip, right? So this, now the blue is ht minus tau, right? Sorry, my bad. The blue here, right, this is h minus tau, right? H tau is the same thing as ht, x tau is the same thing as xt. H minus tau, flip it around along the t equal to 0 axis. And ht minus tau is going to be this thing moving up and down the time axis. Right? So we have that here. Right, and we have everything else that we want to look at. We have the equation for h, we have the equation for x. So we go ahead and we evaluate the integral. So the first thing, you flip, then you slide, and then you look to see what happens. So anytime for t less than 4, remember h, the red one, and I'll use a slightly different color. Red signal is ht minus tau, and that is the one that is going up and down the t-axis. So as t varies, h t minus tau, as it starts from minus infinity, is going to come all the way up here. And until t equal to 4, that is when this signal, now the first part of the signal, actually overlaps with x or tau. So up until t less than 4, the product of x tau and ht minus tau is 0. So therefore, there's no convolution. Convolution integral, the product of the two of them is 0. Fair enough? That's straightforward. The next part now is at the point where t is greater than or equal to 4. At that point in time now, the product is non-zero. So let's arbitrarily put t at the point you see it there. So we arbitrarily putting t at this point. So what is the overlap? Remember the output convolution is a function of t. So at the end of the day, the answer is a function of t. So that at the end of the day, I could figure out what this is doing at any point in time by substituting an appropriate value for t. Yeah? So the answer is not, the answer is not that we're going to put in a fixed value and have an answer that is y at t is 75 or something like that. It's going to be 75t, etc., etc. So we look at this, and for t greater than or equal to 4, because that's where the overlap starts, x at t, ht minus tau is xt, which is this, ht minus tau. Now let's look at that a little bit. Look at that. Remember what you're doing. Let me just go back here a little bit. Ht minus tau, let me go back one slide here. Right. Ht is 0.5 e to the minus 0.5 t. T minus tau, what I'm doing when I flip it around is to take t and replace t by t minus tau. Right? So wherever I have t, I put t minus tau into the equation. So in other words, this is what I now have. When I have t minus tau, this is what the flipped version is. Yeah? So that's why when you come here to the integral, the expression here now is t minus tau at that point. So you're integrating 0.75, right? X is just a simple, X is not a function of t, is a unit step, and it's a step, and the amplitude of the step is 0.75, and h is 0.75 e to the minus 0.75 t minus tau. So you do that. And look at what the lower limit is here now. Remember, the convolution starts from minus infinity, but we said up until t equal, once t is less than 4, there's no integral, there's no overlap. The convolution limit starts at 4, and the upper limit will be arbitrarily wherever t happens to be. T is supposed to go all the way up to infinity. All right? Go here. And if you evaluate that now, well, you get that at this point in time, that yt is 0.75, and if you integrate that and do all the math and so on, and assuming that I'm correct, the answer is this bit here. And we put this in for correctness to indicate that the system doesn't do anything. This is shorthand for saying that the system does not respond for t less than 4, right? Or you could have written it down, if you didn't put that, if you could omit this and you could put for t greater than or equal to 4, right? So you get this answer when t is greater than or equal to 4. You put this inside of here, or the sort of mathematical shorthand means is that this only, sorry, this should have been, by putting this here, it means that the system only responds for t greater than or equal to 4. For t less than 4, there's nothing. All right? And if you were to plot it out now, so here now I could figure out, once I have the convolution answer here, if somebody was to ask me, well, what is the system, what's the temperature of the system now after 15 minutes? I just put T equal to 15 in here and see what it is. If I want to know after 5 minutes, I just put T equal to 5 and I could actually get the answer inside of there. If you look at it and you actually plot it, you see that it takes about 6 minutes to get close to the temperature. So you make a 0.75 degree change on the input. It takes about 6 minutes before that is manifested on the output itself. So you're getting the idea of the input-output relationship here. This is what you're aiming for. The description, we started off with a kind of block diagram description. So you're going through the whole process here. Fair enough? Questions? Any questions? Of course, when you start to try some of the problems, and we'll come to them in a little while, and I'll tell you the particular cases that we will pay attention to as we go through. All right. So some of the properties of the convolution, and this is nice for us. First off, that the order of the convolution, whether you convolve, which is the verb for it, right? And I'm sure in the English expression you've heard when you give somebody a convoluted experience, convoluted explanation, somebody asks you for something, and you give them a convoluted explanation. Well, now you know what you're doing. You're flipping and sliding and doing all kind of things in the explanation instead of getting to the point. All right. So that's where it came from. There you go. So X convolved with H, remember the asterisk is the shorthand for meaning convolved. X convolved with H and H convolved with X are the same thing, right? What is X convolved with an impulse? To find out that, you evaluate the convolution by X tau delta T minus tau, which is the same impulse. You flip an impulse at delta tau, it's the same impulse going to be at tau equal to 0, meaning the axis. And because of the shifting property of the impulse, remember this is now going to be an impulse shifting up and down the time axis continually. Going to be shifting up and down the time axis continually. And what does it do? The impulse function sifts out all of the values of another function once you find the product of the two of them. That's the property of the impulse. So this is going to continuously pick out all of the values of X tau. So in other words, if you convolve a signal with an impulse, you get back the signal itself. Okay? So in other words, you do anything. That is actually important for a different reason. If you shift the impulse around, it means that you could actually shift the entire signal in a different zone in time, and we'll talk about that. Associativity, if you remember some of those words from your math, I keep forgetting them, but anyway, what this means is that if I have this is a system that has two transfer functions, right? Remember, we spoke about that terminology before. We call it cascade. So one block doing one thing, another part of the system doing another. This one, so the system therefore has two transfer functions, an H1 and an H2. You have an impulse coming in, you have an input coming in, xt. So xt convolved with H1 is the output of the first response at this point here. Oops. Let's undo that. Get a different color. Right. So at this point here, that's x1, x convolved with H1. That input goes into H2 now, and y is now x1 convolved with H1, and that convolved with H2. Well, because of the associativity property, what we could do is to convolve H1 and H2 first, and then do the convolution with X. Okay, it's a cascade system, and we make a lot of use of that actually in the Laplace domain, right? So in something like this, if I had to type this out in the S domain, it would be XS H1S H2S, right? And it didn't matter H1S by H2S. It doesn't matter if I put this as H2S multiplied by H1S. Okay, the sequence doesn't matter, which is good for us. And the other one is a distributivity function, which means that if you have two systems, if you have a system where you have an H1 and an H2 in it, that you can break the system up into what we call a parallel system. So you could run it, you could convolve X with H1, and then you can convolve X with H2, and then add up the answers in the end. This is parallel processing, and we also do this a lot in engineering systems. It breaks up the work of the system. It makes the system work a lot quicker. This is a much faster operation than this. All right, so, and it's also simpler to implement at certain things. And when you're doing a microprocessor programming and the like, you're going to meet these things a lot. Parallel systems, and then in control systems, you meet the cascade systems a lot. All right, but the whole idea is the properties of the convolution. So you could always take something that looks complicated and break it apart to make it a little bit simpler to work. So let's look at some examples here, right? We'll just run through this one and at least the approach to it, and you will actually try it. Now, just as an aside, the kind of things that I expect us to be able to do as we go through this, to be able to do mechanically, right? Meaning the flipping, sliding, integrating part. First off, finding the convolution of two pulses, as you see on the screen here. Finding the convolution of two pulses where the pulse widths are the same. So xt and ht are the same width. So two rectangular pulses where the same width. That's the first scenario. And of course, both of them starting at 0 and running to, in this case, 2. So that's the easiest one. The other one that you're going to have to know is where the pulses are the same width, but one is starting at t equal to 0 and going positive, and the other one is symmetrical about t equal to 0. So like in this case, is running from -1 to 1. All right. The other one, let me just clear this. The other scenario we're going to have to look at is where the pulses are not, they are rectangular pulses, but one is bigger than the other. So one might be like this, right? So one, either the H or the X, is larger than the other one. And then the next case, of course, is where one is larger than the other one, but it is symmetrical about the origin. Yeah? Fair enough? And then the final ones that we're going to look at that you need to pay attention to would be these kinds, where you have a rectangular pulse on one side, okay, and a triangular pulse on the other side. And the variation of this is going to be where either both of them are the same size, either the pulse or the triangle is bigger than the other one, and then is it symmetrical about the origin, or is it not symmetrical about the origin? Yeah? So if you could do all of those, this one, and then of course there's the most complicated one, and we'll do those in the problem sets I think there's one in the problem set where you have two triangles now, right? That one is in terms of, and the complexity in this thing has nothing to do with the convolution itself. It has all to do with a little bit of calculus. How do I get the equations to integrate these things? All right, so those are the scenarios that you're going that we will cover in class or in the problem sets as we go forward. Right. So to do this, right, let's just have a look at class this particular one here, just to run through the process itself. The first thing you need to do is graphically you draw it out. So this is ht, this is xt. You need to define xt equal what? ht equal what? Right? So how you define this? xt is equal to 1 for t less than 2 and greater than or equal to 0. Yeah? Fair enough? Notice how I have it. It is equal to 1 for t less than 2 and greater than or equal to 0. Remember, we change at the limits. So t at point t equal to 2, x has gone back. That is this point right here. X has gone back to 0. All right? So x is 1 for t be less than 2 or greater than or equal to 0. Similarly here, ht, right, is equal to 1 for t less than 2, greater than or equal to 0. So that's the first thing. Your step one, you draw it out, right? Or well, if it has been given like here, if you don't draw it out, you put it, you have it down right underneath the first thing. You have the equation for xt and ht. Step two now is to change t to tau. Changing t to tau on this is nothing. Xt h tau is going to be the same thing. Then you're going to convolve. You've been asked to find a convolution of x and h. You could decide which one you want to flip around. Remember, the problem doesn't, the properties of the convolution say that you could do x tau, h tau, or you could flip around h or you could flip around x. It doesn't matter which order you want to do it. Both of them are the same, so pick one. Let's do what we've looked already in class. So let's find ht minus tau. So if I were to flip around this, first off, h minus tau will look like what? H minus tau means that we're flipping this around the t equal to 0 axis. So if I flip it around the t equal to 0 axis, there we go. Very good. So the t equal to 0 axis means that ht minus tau is going to look like this, right? It's going to go from 0 to minus 2. All right? So this is ht minus tau. Right? And this is my x tau here. So the last part now is to do the convolution, and you do the convolution by identifying, always you identify the zones of overlap. Zones of overlap. Right? Yep, from t minus 2 to, so it's going from t minus 2 to 0. Yes. So the zones of overlap, just like we did for the little temperature controller example, the first thing is that the zone of overlap here, let me just clear this a little bit and draw back. So if I do it, we have x here and we're convolving x with right? So this is ht minus tau, and the blue is x tau. Right? So as this is moving along the place, as Sajad pointed out, right, this point here is t, this point here is t minus 2. Remember the width of the pulse, the width of the pulse is 2 units. So wherever the front of the pulse is, the back of the pulse is t minus 2. There's 2 units behind that. So the zone of overlap, the first zone is that for t less than 0, remember you're integrating with respect to tau, and the limit is that as t goes up and down the axis, for t less than tau, there's no overlap. Fair enough? So if there's no overlap, the convolution of x and h is 0. So zone 1, and you would write it down, zone 1 for t less than 0, the convolution is 0. We keep sliding. Remember, t is continuously varying. So the next time t appears, as t goes here, as t gets bigger, t is going to do this. This is t. This is t minus 2 there. All right? So where's the overlap zone? The overlap zone is that zone there. So the next part of it now is that for t greater than or equal to 0, and remember, once this moves, the back half of the pulse is following, and at the same time t minus 2 less than 0, right? That's the zone. Then you have the integral here. And what is the convolution? Is the integral of x or tau, which is 1, h or t minus tau, which is 1. What is the upper limit? What is the overlap zone? T here and 0 here. Yeah? Make sense? Yeah, no, maybe? Right? And if you integrate that, if you integrate one as t, so that between the two of them, the convolution, if you integrate this, the convolution is t, and the zone of overlap, this in shorthand, is t less than 2 greater than or equal to 0. That is what this becomes. And this keeps going and going and going. So then the next bit that we have is this. All right, so this is t. This is t minus 2 here. So where's the zone of overlap now? The zone of overlap is between here and here. All right, so what are they again? So in this case, t greater than or equal to 2, t minus 2. So t is greater than or equal to 2, t minus 2 less than 2. All right? So if you do that, that means t is between 4 and 2 now. And what's the integral here? The integral, the upper integral, look at the actual zone here. When you're integrating, the upper limit now is 2. The lower limit is t minus 2. And you're integrating 1 by 1, because x and t are both 1 each. Yeah? and you work out whatever that is supposed to be. And the last bit, of course, is when H has gone here now. And this point is when T minus 2, remember that is this point here, T minus 2 is greater than or equal to 2. In other words, when T is greater than or equal to 4. At that point in time, the convolution here is equal to 0. So if you work it out, there are 4 parts to the answer, therefore. Right? Part 1 of the answer the first part, which is before here, the answer is 0. The second part, when it is overlapping, the one pulse, the HT coming over X. So the answers you could see as you move, as HT minus tau moves over the X tau bit, as you could see, as this moves, this overlap area is going to increase until eventually it gets to a maximum. And then as HT minus tau keeps sliding along the x-axis, right, it starts to do this. So this gets smaller and smaller, and it goes down. And if you were to watch, so if the actual convolution, therefore, starts at 0, it goes up to a maximum, and then it goes down to a minimum, and then comes back to 0. Right? This is at 0, this is at 0.2, this is at 0.4, and greater than t equal to 4, there's no overlap. Yeah? Questions? And I'm sure you have, right? But I need you to listen, at least to go over the slides, or to do it again mechanically. This is the simplest of the convolutions. 2 pulses whose width are the same and whose the equations are the same. Right, so the last part, which last part? You mean about the overlap and what happened to the convolution? Is that it? Jade? When you said the last, right, okay, good. So we have the 2, and as H, as we said, right. So this is my H T minus tau here. This is moving, right? This is moving along the axis. So in terms of the answer to the convolution, before 0, exactly, yeah, because it's a product. So if one of the products, if there's no overlap, it means that the product multiplying one by the other can't exist. They don't share the same time zone. But back to the question that Jade asked. So you're looking at the convolution. So as HT minus tau is sliding, before 0, there's no overlap. So the convolution is 0. Okay, now let's draw it out graphically here. Right. All right, so we're going along our time axis here. At 0, there's no convolution. At 0, the convolution is there. It increases because H is doing this. Remember, the convolution is the area. So as H moves along, the area of overlap gets bigger and bigger until 1H is totally on top of X. That's a maximum overlap. Think of your 2 hands going over each other. Right? At one point in time, one hand is going to entirely cover the other one. That is a maximum overlap, and that's where the convolution reaches a maximum. And then after that now, as H moves along, the area of overlap is going to now decrease. until at some point in time, H is now here, and there's no overlap any longer. So graphically, the convolution starts at 0, reaches some sort of maximum, goes back down to a minimum, and then departs. And the time zones, if we had it correctly, here should be 2, here should be 4. And then after t equal to 4, there's nothing. Yeah? So see, we're running we're running a little late here, so I don't want to get into the whatever other class you have. So I will stop the lecture today. At this point in time, we will run through some other examples and look at it in some more detail tomorrow as well. Okay? All right. So